Time's 11 o'clock, so let's get going here. So project number 1 was graded. All of you hopefully have seen your project number 1. Well, it's been a brief amount of time at the beginning of the class period talking about project number 1. Project number 2, I posted it this morning. Since that doesn't necessarily give you enough time to have to download a copy and bring it with you to class, I'm going to postpone discussing project number 2 until Tuesday. We will continue in Chapter 3 today. Also, when we get done with Chapter 3, I expect that there will be a test over Chapters 1 through 3. So, again, a tentative date would be October 2nd for our first test over Chapters 1 through 3. Maybe 4. Chapter 4 is very, very short, so that's why we might be able to squeeze Chapter 4 in there. But start getting ready for a test coming up. So are there any questions before we get going here? Okay, why don't you take out your project if you have it with you. Just a few small comments I want to make. Overall, the grades were very good, as you saw from the mean score. In fact, I think every student got an A on it. So that's a good way to start the semester. I guess 3 things I want to talk about. First of all, if you are working in a group and if you email me the project, I will only email it back to the person who emailed it to me. So after I grade it, I will only email it to the person who emailed me. Unless you had copied your other group members on the email that you originally sent to me. Then I will do a reply to all so that all students in the group will get the project at the same time. So I do recommend that you do copy all students on any, all group members on any emails that you send to me when you turn in your projects. That way everyone gets the project back at the same time. Is that clear? Because I don't think I explained it very well, but is that clear? Okay, I will. Silence means yes, so let's move on. Part G, this, I don't know, maybe was the most missed problem. I mean, there wasn't that many missed problems on the exam. But Part G says the following. Suppose the acetic acid content was listed on the package for each individual block of cheddar cheese. Also, an estimate of taste is given in the form of both a confidence interval and a prediction interval using the previously found regression model. If you were going to purchase a block of cheese, so you see an actual block sitting on the, sitting at the grocery store up on a shelf, which would be more important to you, a confidence interval or prediction interval? Well, the prediction interval will be the more important one. Because basically that block of cheese that you see up there is a YH new, and it's a random variable. And you want to have some kind of measure of, well or how good is it going to taste. So that particular block of cheese, that's why you would take the prediction interval. Now the confidence interval for this particular problem, again, gives you a confidence interval for the expected value of YH new, meaning that on average, like if you were to look at all possible blocks of cheese out there and somehow we're able to average all this measure of taste, that's what the confidence interval gives you. And that's why you wouldn't be as interested in that as you would the prediction interval, which gives you a prediction for one block of cheese. Are there any questions about that? Yeah.
I think it's true that it's a block of cheese, but because our model is a statistical model, we want to have some sense of knowledge about the average, because you might have another block of cheese with the same amount of acetic acid.
But it's still 2, not an infinite number. Can you purchase an infinite number of blocks of cheese?
No, I can't, but the statistical model is based on that. The population, right? So when you build the statistical model of your taste versus acetic acid content, so you're looking to a sample that is greater than 1, right? It's not the whole population, but you're looking into a big sample. measure the cheese blocks. So that's why I thought confidence.
But I mean, in the end, you're only buying one. And you're interested in a y. You're interested in a random variable, not a parameter.
But you are using the parameters that have been estimated by looking at your sample, right?
And you need to take into account then the variability that epsilon gives you. And by looking at confidence interval, you're not fully taking that into account. So we can talk about it more if you want to after class. There's one other thing I wanted to mention about this. Okay, also, if there were some students who were saying, well, you would take the confidence interval because it's shorter in width. Well, yes, we want shorter in width intervals, but that has nothing to do with which is more appropriate for this problem. You're interested in the random variable, not the expected value. So, any other questions? I'd be happy to discuss it more with you. Okay. Lastly, this is the extra credit problem. And it just worked out great that for the new stuff that we're going to talk about today in class is we're going to talk about some stuff that's closely related to what was needed for the extra credit problem. A number of groups attempted it. Some of them were successful, some of them were not. Please, first of all, note this small little typo there in the answer key. That beta hat 0 should have been B0, beta hat 1 should have been B1. And what I asked you to do basically was to simulate a sample size n equal 30 from the sample regression model 1 and then use a particular seed number so you can reproduce the results. And the reason why I ask you to do this is because it helps make sure that you fully understand the assumptions behind our regression model. So, again, as we have seen many times before, this is what our regression model looks like. My ability to draw sigmas is not very good. So, y sub I. So this is our response variable. And basically what this problem is saying is, show me how you can simulate y. It's equal to beta 0 plus beta 1 times x sub I, your predictor variable. And remember, at least at this point, when this project was first introduced, we always said that x's are constants. Where did the x's come from? Well, our observed acidic acids for our data. Plus epsilon sub I, which is independent normal 0 sigma squared. Okay, well, so one of the main keys then is understanding this epsilon part, because once you have the epsilon, you can basically get what y is, because beta 0, you use B0, beta 1, you use B1, and the x is the acidic acids, since you're simulating data from this particular model. So what we need is some way that we can simulate data independently from a normal 0 sigma squared. When I introduced the project to you, I showed you how you can use the R norm function to do that. Of course, what do we use for sigma squared? Well, what we use is estimate, MSE. So what I did then, as shown here in the answer key, was basically to form my simulated responses. Let's call them y stars just to be different from our regular y. I took beta 0 plus, I took B0 plus B1 times x plus then a simulated normal random variable value. And that's how I form my y's. So then here's the actual code. First thing I do, suppose my results from the LM functions in an object called mod.fit1. I summarize it, put the results into sum.fit1. I set a seed. And then, to find y star, I basically put this formula, or this equation, into the correct syntax. So again, B0, B1, my x's, and then here's the R norm function. N is 30. Since I had a sample size of 30 originally with this sample. Here's the mean 0. And here is the standard deviation, which comes about through taking the square root of MSE. Remember, we can pull that square root of MSE out of that sum.fit1, as we've shown in the past. Now let's make sure that we understand what R is doing here. B0 is one numerical value. B1 is one numerical value. But look at this cheese $sign acidic. Cheese is my data frame that contains the x's. Notice this has 30 values in it. So how does R react then? Well, when it takes B1 times x, it basically takes B1 times every single x value. So now you still have 30 values. And then also, B0 is one value. How does R react? Well, it takes each of the B0 value, it takes the B0 value and adds it to each of the 30 different B1 times x values. That's how R does its processing. And then, of course, R norm here is going to have 30 values in it as well. With that, I get my Y stars. So this is a simulated set of responses. And just to kind of look to see, well, is my data that I simulated reasonable? Well, how about we plot it? So here are my Y star values. Here are my X's. And you can see, if you compare this plot to the plot that you did earlier in the project, you can see that it looks like the data is somewhat similar. I mean, obviously it's not going to be exactly the same, but it's going to be somewhat similar. So that's one way that you could do to actually simulate data from some kind of estimated model. Here's a slightly easier way to do this data simulation. Unfortunately, though, it takes away from the fact of you needing to know exactly what one of these regression models means in terms of the assumptions. And that is, there's a nice little function R called simulate. So if you say simulate object equal mod.fit1, where we have our B0, our B1, and also the stuff in there allows you to calculate our allows you to calculate the MSE. Number of simulated data sets, 1. Here's my C number, and look, we get exactly the same data. I can't show both at the same time. You get exactly the same data. Obviously, the simulate function is easier. It was good to see that some students actually found that, even though I never had mentioned that before in class. So that's how you can simulate data from a model. Any questions? So we're going to be doing that in like 10 seconds. Any questions? Okay, let's move on in the notes then. As I said, project number 2 is out there. I think I failed to mention in class, the project's going to be due on Tuesday, September 25th. You're welcome to get started on it now, even though we are not going to discuss in class yet. The first few parts of the project, it's based upon the second half of Chapter 2 material, and then the rest of the project's on Chapter 3 material that we're doing right now. You will note that in this project, I do mention a particular function of mine that I've written that I want you to use. This function, if you want to get started on it, is discussed in the Section 311 notes. Okay. Let's see here. So we were looking at 6 different things regarding our model and how we could use residuals to help us evaluate if some of our model assumptions or if there are problems with our model, if these problems occur. And we had just started talking about the regression model is not linear. Our residuals will help us determine if the regression model is not linear, which then would be a violation of our model. The reason being is because, again, this is what our model looks like. This is just a different form of our model. The expected value of y is equal to beta 0 plus beta 1 times x. Of course, maybe instead of that model, maybe we need a square root of x in there instead of x. Or maybe we need an x squared in there. And so by looking at the residuals, it helps us make that evaluation. And in particular, we look at a plot of the residuals, or e's, versus x. If the points appear to be a random scattering, great. Looks like there's not evidence against problems with our model. I'm sorry, I didn't say that very. There's not evidence to suggest that there are problems with the model. If there's some kind of a pattern in the points, then what that says is that there is perhaps a misspecification of the form of the predictor variable in the model. And often the shape that you see in this residual versus X plot leads you to some idea of what kind of maybe transformation is needed. So we were looking at this power load example last time, and this is what our data was. So power load was on the y-axis. On the x-axis we had temperature. And you can see in this simple setting that maybe there's a little bit of a curvature there instead of just a straight line. Here's what the estimated model looks like when we did apply the residuals versus temperature. Well, it looks like we have some kind of pattern that looks like that. If I were to draw a line in the middle of it. It's not the best line, but I think you get the idea. And what that's saying that there's a problem with our model. And in particular, when you see shapes like that, that might indicate that maybe you need a quadratic term in your model. So like a temperature squared. And so we try to include a temperature square in the model. And this is the output that we got when we included temperature squared. Remember the weird syntax we need to use in order to include a temperature squared in the model. Then when we looked at the residuals versus temperature again with this new model, now we have a nice little random scattering of points. Everything is great. And in fact, when you look at the plot of the model through the data, you can see how now the model goes to the middle of all those points, indicating now we have the correct specification of the predictor variable in our model. Okay. So that leads us then to where we left off. Okay. So to help give you a variety of examples, what I decided to do is actually simulate some data from a regression model, where sometimes my data simulation corresponds to the model that we've basically assumed so far. Expected value of y is equal to beta 0 plus beta 1 times x. But other times, I'm going to simulate data from a model like expected value of y is equal to beta 0 plus beta 1 times square root of x. And look at, if I were to ignore the fact that I knew it was a square root of x there, and actually estimate the model with just x itself, look at what happens. Hopefully, that residual versus x plot is going to pick up the fact that I have misspecified the model that I'm estimating. So, to begin here then, how about we look at the simple case where everything is okay. So, here's my model. Since I need to simulate data, I need to choose beta 0, beta 1. I just happen to choose these values for no particular reason. Also, I need to choose a particular value of sigma squared here, since I'm actually picking the model myself. So how about sigma squared is 625? And I need some kind of x's here. Well, I don't really necessarily have anything to go back to for my x's, so how about we simply take the x's to be a sequence of numbers from 1 to 99 by 2. So I think we might have looked at that function before, the SEQ function, but in case we hadn't. So SEQ stands for sequence, and I'm going to do a sequence of numbers from 1 to 99 by 2. Put that into x, and just type x, and there you go. You see it. Okay. Now I need to simulate data from which I can, from this model. And then I'm going to estimate a sample model with this data. So I'm going to set a seed so I can reproduce my results. And then epsilon 1 is going to be corresponding to this epsilon random variable that we talked about. R norm n equal length of x, just so that I have the correct sample size. Mean is 0, standard deviation 25. I'm going to choose beta 0 and beta 1. And then to form y, I'm going to call it y1. I'm going to take beta 0 plus beta 1 times x plus epsilon, just like what we did with the extra credit in the project. So those are all my y values. Now let's estimate the correct kind of model. LM function formula equal, there's my response, here's my predictor variable. Note that unlike what we usually do in the past, I do not have a data equal argument there. And the reason being is because y1 and x exist outside of the data frame. So I'm directly specifying where my data is. That's why I can do that. If I wanted to, I could have put y1 and x into a data frame and use the same syntax that we've done it before, but it doesn't really matter. I'm going to put the results into mod.fit and then take a look at the parameter s-fits. Or in other words, the b0 and b1. This is what we get. So based upon what I chose for beta 0 and beta 1, do you think these are reasonable values? What would we expect b1 to be approximately? Look at your notes if you need to. 10. Well, look at that. We're getting about 10. That's great. What about b0? It was 2. Yeah, it's a little bit higher than in fact, it's a little bit higher than I expected. But again, there's going to be variability from one sample to another. In fact, I could go simulate another data set, and maybe I'll get a b0 that's closer to 2. Try that on your own. It's a very good experience. So this is what my sample model is. So I'm sorry, I shouldn't say this is my sample model. It's probably more appropriate to say that this is my sample model. And it's estimating the expected value of y is equal to 2 plus 10 times x. Okay? So the sample model, population model. So in this particular case, I'm actually estimating the correct kind of model because the way that we simulated data, we just had x there, and I'm estimating the model the same way. So what would you expect then in these plots? Well, like what we would see here. Left-hand side, we have our values of y versus x. I have the regression model on it. You can take a look at the code on your own. It's basically the same kind of code that we've used before with the plot function and with the curve function. And you can see, yeah, the model seems to be doing what we would expect. Residuals versus x, a random scattering of points. Good, great. Everything is as we would expect. All the model assumptions were satisfied. Good. Okay, well, let's look at what happens when we don't estimate the correct kind of model. So now let's say that the way that I simulate my data is exactly the same as before, except for I have a square root of x in there instead of x itself. And also, just to get some numerical scaling right so that the plots look nice, instead of using, make sure I got that right. Hold on a second. Small typo. That shouldn't just be 5 here. It should be 5 squared. So instead of using a variance of 625 like I did before, now I'm going to use a variance of 25. So I can simulate the data in the same kind of manner as I just got done doing, except for the change to the predictor variable and the change to the variance. And here is what my sample model looks like. So what do you think about B0 and B1 in comparison to beta 0 and beta 1? Looks like they're off. Well, again, I'm estimating the wrong kind of model. Notice in my my LM code, I just have an x there. I don't have a square root of x. Just to make sure it's clear why I'm doing this. I'm estimating the wrong type of model to show you what happens then in one of these residual versus x plots when you know you have the wrong model. This is why I'm doing this. So I can do the same kinds of plots as before. Obviously, on the left-hand side here, it doesn't look like that straight line is capturing the true relationship, or it's not capturing the relationship between x and y very good. If you take a look at my code, y2 is the response variable. That's why I have a y2 there versus just y. On the right-hand side plot, we see the residuals versus x, and we can see some kind of pattern that's forming. Something that looks like that, maybe. If I were to draw a straight line, no, not a straight line, but a line through the middle of points. So, this diagnostic plot that we've been talking about has picked up the fact that we have estimated the wrong model. Well, what would happen then if we did estimate the right model? So, what I'm going to do when I estimate the model using the LM function, I'm going to simply put this in, SQRT for square root of x. Here's my B0. Here's my B1. Again, the original values of beta 0 and beta 1 were 2 and 10. So what do you think about B0 and B1 here? Not bad. Again, B0 estimates beta 0, B1 estimates beta 1. Let's do the same kinds of plots. What do you think of these plots? Looks pretty good. Notice how the residuals versus x there looks like a random scattering of points. And again, this is what we would expect when we have specified the predictor variable correctly in our model.
Question?
Yeah.
What happens if we just add like the x squared? Like when you look at the data, it seems like you have like a parabola.
Perhaps that might be a reasonable approximation to what we want to do. I don't know. Let's see. I haven't done that before. Make sure I have the data simulated. Hold on. Looks like it's not as good. We can still see some kind of trend there. But this then leads to a point that I was going to eventually make, and that is it's it can be difficult figuring out what the correct transformation is. In the book, and please make sure you do look at this on your own. In the book on page, I have the reference in here. Where is it? Page 130 in the book. What the authors do is they give you a number of plots of the residuals versus x, along with what kinds of transformations of x would be helpful. You can use that as a starting point to try to figure out what kinds of transformations would be helpful. What I often will do is I'll just try some common transformations, such as square root of x, x squared, maybe natural log of x, and see if this helps my residual versus x plot. So that's the way that you can approach trying to find which transformation works. And to be honest, there may be more than one transformation that seems to work. Of course, there's only going to be one transformation that's totally correct, but there may be other transformations out there that may seem to work reasonably well. And again, everything that we do in statistics is an approximation anyway. You know, if everything seems to work relatively fine, okay. Okay, let's see. So page 319 then. So in addition to square root of x, often in these kinds of situations a log transformation will work out too. Even though obviously in this case we know what the correct answer is in terms of should be square root of x. But sometimes a log transformation will work out well in those kinds of situations. Here's another example. Suppose that this is my regression model now. Y is equal to 2 plus 10 times 1 over x plus epsilon, where epsilon is distributed independent normal 0. That should be 5 squared there, or 25. So what I decided to do is I simulated some data from this setting. In this particular case, I chose slightly different x values just to make sure that things look nice on a plot that I would present to you. That's the only reason why I did that. I simulate the data otherwise in a very similar manner. Notice my response variable is going to be called y3. And here's where I put the 1 over x in there when I simulate the data. I'm going to estimate first the wrong model to see if my residual versus x plot picks it up. So I estimate my model. Notice that my estimated model gives me a B0 and beta 1 that are quite different. B0 and B1 that are quite different from beta 0 and beta 1. Here's a plot then of the resulting model on the left-hand side. On the right-hand side, we have residuals versus x. Do you think we have any problems? Yeah, we do. Okay. So, how about now we estimate the right model? So now what I'm going to do is estimate the model so that I do have 1 over x there as my, what I'm using basically is the form of my predictor variable. Note the syntax that I have to use to estimate this model. Similar to what we had seen before with an x squared, you do have to use the I function here to get R to recognize 1 over x correctly. So please be aware of that. So now I estimate my model. Here's my B0, here's my B1. Again, remember what beta 0 and beta 1 were. Well, that looks pretty good. You know, I'm getting what we would kind of expect. I can do a plot of my model now. Well, that looks pretty good. I can also do a plot of the residuals versus x, and again, I get a random scattering of points because I have now chosen the correct model. Note, in situations such as you see a plot like this, another kind of transformation that will often work well is e to the negative x. Now, how do you do this e kind of transformation R? Well, there's an exp function that allows you to do it. How do you do log transformations? There's a log transformation. So if I say log of 1, log parentheses 1 in parentheses, I get 0. The log function by default does a natural log transformation. There are arguments in the log function that allow you to do other log-based transformations. Okay. So that concludes then talking about misspecification of your predictor variable in your model. So just to review, how do we determine if we have the problem? Do the plot of the residuals versus x. If it's a random scattering, okay, great. If it's not a random scattering of points, then you might want to explore various transformations of x. Okay, so we're going through 6 different things that we can do with our residuals to examine various aspects of our model. Here is number 2. We've already talked about just number 1. The error variance is not constant. Remember, in our way that we specify our model, let's say if you have a sample size of n, each of these epsilons, epsilon 1, epsilon 2, down to epsilon n, has to have exactly the same variance. And this is often referred to as the constant error variance assumption. Well, there are times where this assumption is not going to hold true. Fortunately, there's a variety of things that you can do to fix it, or fix the problem. We'll discuss those as we go along. But a way that one could use in the residuals to help diagnose the fact that there is a potential problem where the variances are not constant, maybe, for example, epsilon 1 has a variance of 1, epsilon 2 has a variance of 5. The ways that you can diagnose that is, again, to look at a plot. This time, residuals versus your predicted variable value, your y-hat. Okay. So here are 2 examples. Now, when we only have one predictor variable, in addition to using residuals versus y-hat, one can get a general idea that there's a problem by looking at a plot of y versus x. Starting in Chapter 6, we'll have more than one predictor variable, and we won't be able to do plots like this anymore then. Imagine if you had 10 x's, or 10 predictor variables, I should say. It's hard to do an 11-dimensional plot. So in this particular case, here's an example when the constant variance assumption holds true. I simulated some data where it was true. I did a plot of the data, and you can see how the points are roughly, the same amount of variability around the line as a function of x. So you can see the variability here is similar to the variability up there. Now here's an example when the constant variance assumption will be violated, where, again, as a function of x, the variability here is very, very small. But the variability for larger values of x, a lot more variability. What that's telling you is that your sigma squared is changing here. And again, typically we will always use this kind of a plot. Your residuals versus y-hat to help diagnose the problem. As long as we're talking about one predictor variable, we'll also take a look at the y versus x plot too to help make this make sense. But this is what a plot would look like if you have a violation of this constant variance assumption. As a function of y-hat, you can see how the variability is increasing as y-hat is getting bigger and bigger and bigger. So the spread of those points is getting bigger and bigger. And you can see here, it kind of looks like a funnel. So this is if I were to draw a line around the edges, a straight line, I didn't do that very well. But you can see with the blue lines that I have there up there, you can see it's kind of a funnel shape. Cone shape, some people will call it too. This tells you got a problem. Another version of this plot where it shows you have a problem too is that let's say E was here, let's say y-hat was here. You might have something that looks like this. Where you can see now in the middle, you have a lot of variability, and on the edges, you have a lot smaller amount of variability. Again, this tells you have a non-constant variance problem. We're somewhat making subjective judgments here from looking at these plots. So you have to be careful when looking at these plots. I think it's natural for us to see patterns there or certain shapes when they may not necessarily exist. So take a look at the following kind of plot that sometimes you will see. So here's E. Here's y hat again. Do we have a problem with non-constant error variance here? Obviously, on the right-hand side, it doesn't look like it of that plot. To make sure you see what I'm talking about. Purposely drew it like this. On the right-hand side, the green part, doesn't look like we have a problem. But then when you also take into account the ones that are colored in yellow, you might be thinking, oh, well, the variability over there is a lot less than the variability on the right-hand side. What do you think maybe caused the fact that we see smaller variability on the left-hand side? Perhaps the answer is too obvious, but I'll ask the question anyway. Well, what do you think? Why do you think we're seeing less variability on the left-hand side? Excuse me? Yeah. We have a lot less observations on the left-hand side. So maybe, in fact, for the lower values of y hat, if I would have had a larger sample size, I would have actually seen this large amount of variability. But since I only had a sample size of 2 there, I'm not seeing it. So if I had a plot like this, would I be worried about the constant variance assumption? Probably not. Because there's really not enough information on that left-hand side of the plot to make a judgment. Now instead, if I would have had something like this, now I would be a little bit more concerned. So now I do have a larger sample size. I have more information here to make my judgment in comparison to before, and I'm still seeing the same amount of variability. So be careful when you look at these plots. So what can we do? What can we do if we think there might be a problem with this constant error variance assumption? Well, we do kind of like what we did with the predictor variable problem. We do a transformation. Here are the 3 most common transformations that are typically applied. Where the very first one there, that's a natural log. Natural log is the most common. Natural log works nicely many times. But sometimes maybe inverse transformation, 1 over y would work. Or square root of transformation y. And to emphasize what I mean by these transformations, that instead when you estimate your model, you don't use just y itself, you use, for example, the log of y. You'll see examples of that coming up. So that's the first thing that you could do. The second thing, which we will also talk about shortly, is to examine what's called the Box-Cox Family of Transformations. This is kind of a method that can be used to try to estimate what kind of transformation will work best. And lastly, we're going to talk about in Chapter 11 another way to approach this problem, and that is to basically abandon using least squares estimation itself. There's a whole bunch of other ways that one can estimate a regression model. In this class, we focus mostly on least squares to get B0, to get B1, in order to do all the inferences that we do, the confidence intervals and hypothesis tests. There's other ways that you can estimate these models. And Chapter 11 starts talking about those. And one of the methods is something called weighted least squares, where this allows you to incorporate this extra variability. The fact that maybe sigma squared is different for every epsilon allows you to actually incorporate that into the estimation process, and then also into the inference process as well. There are some problems, though, that pop up with how to do that, but still, it's another solution. So before we get to an example, let's talk about this Box-Cox transformation. Now, in order to fully understand Box-Cox transformations, you need to know what maximum likelihood estimation is. Some of you probably do, some of you may not. Maximum likelihood estimation is typically talked about in a Stat 880 course for non-stat majors or Stat 883 for stat majors. If you haven't had those courses, then maximum likelihood estimation may be kind of foreign to you. Those courses, of course, are not prerequisites for this course. So instead, what I want you to get out of this Box-Cox transformation discussion is the idea of how to apply the results correctly. Okay. This is the book's notation. I don't think it's the best, but this is what the book does. So here's our model. And instead of just using y on the left-hand side, we're going to use some kind of transformation of it. And our authors denote this as a y with a superscript lambda. The reason being is because this lambda is going to be actually a parameter that we're going to try to estimate. So we talked about beta 0, beta 1, sigma squared as parameters. How about we have another parameter called lambda? And this is what this ends up being. If lambda does not equal 0, you're basically on the left-hand side of your model, you're putting y to the lambda power. So for example, if lambda was 1/2, then your model would be square root of y is equal to beta 0 plus beta 1 times x plus epsilon. That would be your actual model. If lambda was 0, then you're working with the natural log, and I put an e here to emphasize that. You're working with the natural log of y on the left-hand side of your model. If lambda was equal to 1, what would that say? No transformation. Now remember that, because that's going to be important coming up. Typically, lambda could be anything, to some respect. Typically, one will search through different values of lambda from -2 to +2 to look for the correct transformation to help solve, I shouldn't say necessarily solve, to help lessen this non-constant variance problem. And the way that this is done is through getting what's called a maximum likelihood estimate for lambda in a particular range that you specify. So maybe I come up with a maximum likelihood estimate of lambda equal to 0.5. That tells me, okay, square root. Let's get an example. This data set that we're going to be looking at involves trees. And what we would like to be able to do is estimate the volume of a tree in terms of its wood, given its height. So y is going to be volume, x is going to be height. The actual data set's called trees, and it's already actually inside of R. It's in a package called MASS. MASS stands for Modern Applied Statistics with S. And basically, this corresponds to a book by the same name, written by two guys by the name of Venables and Ripley. And associated with their book, they have a package. And in this package, they have a whole bunch of functions. They have also data sets that they examine in their books, or in their book, I should say. This used to be probably the most popular book on how to learn to use R. And also its predecessor, you could say, to some respect, S. Remember how I mentioned, I think in my introduction to what R was, how R came kind of out of the development of a language called S. Anyway, though, they have this data set that we're going to be using with it. So I'm going to estimate my model, where I'm not going to do any transformations at first. So I have volume, I have height. I'm pulling that information out of the data set trees. I summarize the fit of my model so that I get y hat is equal to -87.12 plus 1.54 times x, where y is volume, x is height. Let's do some plots. So first of all, I'm just doing plots like what we've done normally in the past, so that's why I'm not going over the code directly. Here's a plot of volume versus height with the sample model on it. What do you think? It looks like a little bit, but the variability that you see down here is smaller than the variability that you see up there. So, you might want to entertain the possibility that you have non-constant variance, maybe look at some transformations. Here's my residual versus y-hat plot. Again, variability over here seems to be smaller than the variability that you see over here. Doesn't look like to be a large violation, but when you have smaller sample sizes like this, again, it can be difficult to make that determination if there is truly a problem or not. Because all it would take is maybe if I had one observation here, maybe one observation up here, then you might be thinking, well, maybe I don't have a problem. Again, this is due to having a relatively, let's say, not small sample size. I'm sorry, not large sample size. So, you just got to be, it can be a judgment call. It's subjective to some respect. But I would say typically that, that there looks like there is some kind of problem. And what I would typically do is I draw a line that looks like this, draw a line that looks like that, and there you see that kind of cone shape. Okay. Now let's try this Box-Cox transformation. Let me get some stuff into R first for my trees.R function. I'm sorry, code. Okay. In the mass package itself, in case I didn't mention this before, sorry. Remember, whenever you're using a new package, that's not like the base ones that we've been using, like graphics, stats. You're going to have to say library mass. This is automatically installed in R, so you don't actually even need to download it at all. It just is one of these packages that are automatically installed. So if I did library mass, head trees, there you can see that. To do the Box-Cox transformation, our goal here is to estimate what lambda should be. There's a function in the mass package itself called Box-Cox. And the first argument says object equal, put in the results from the LM when you're fitting the regression model. And then you need to tell R, well, what are my possible values of lambda that I want to search over? And so I'm going to say lambda equal a sequence of numbers from -2 to +2 by 0.01. I want to focus on just those values. So I'm going to highlight this code and run it, and look what happens. I had a new plot produced. This is on page 330. On the y-axis, we have possible values of lambda. I'm sorry, on the x-axis, we have possible values of lambda. On the y-axis, we have what's called the log likelihood function. Now, for those of you who do not have experience with likelihood functions, maximum likelihood estimation, let me give you a brief explanation of what's going on here. A maximum likelihood estimate is the value of a parameter that maximizes your what's called a likelihood function. Equivalently, you can look at a log of the likelihood function. And so what this plot is producing here is a graph of what the log likelihood function would be if lambda was -2, if lambda was -1.99, if lambda was -1.98, and so on, and drawing this curve then showing you what the possible values of the log likelihood function is. Again, the maximum likelihood estimate then for a parameter is that value of that parameter which maximizes that likelihood function, or equivalent log likelihood function. So we can see that, let me go back over here to Word. We can see that the maximum occurs right about there, right? And if you project down, you can see that this occurs at lambda equal 0.19, roughly, from looking at that plot. I'll show you how you know it is actually 0.19 coming up. So what this says is that this is the most plausible value of lambda given your data. Again, this is the most plausible value of lambda given your data, using this statistical technique called maximum likelihood estimation. So what that means then is that this Box-Cox transformation technique is saying use y to the negative 0.19 power as your new transform response. Not very intuitive to work with, the negative 0.19 power. Anybody worked with a negative 0.19 power in the past? Probably not, unless you've worked with this data set before. But also what this function, this Box-Cox transformation function gives you is notice that we have these other little lines drawn here. And that's about negative 0.8 to positive 0.4. About. And without going into all the details behind this, basically what that is a confidence interval for the true value of lambda. 95% confidence interval for the true value of lambda. Notice that 0 is inside that interval. So what would be what transformation would that correspond to? Y to the 0? That's no fun. What was I showing you before? What would be when lambda equals 0? There was a small change. Natural log. So we're used to working with a natural log transformation, a lot more than negative 0.19 power. So you might want to entertain then considering a natural log transformation for y as well. We will do that too. What do you think about no transformation at all? Can I get away with no transformation? Probably not. Why?
Confidence interval doesn't contain 1.
Yeah, confidence interval doesn't contain 1. Here's 1. Remember how I mentioned a few minutes ago that when lambda was equal to 1, that said no transformation. So it looks like what this is saying then through this technique, that there is sufficient evidence to indicate that you got a problem and that you should try some kind of transformation. Here are the ideas of what kinds of transformations to look at.
Another question?
Yeah.
I'm sorry, I don't understand why, if lambda equals to 0, we're going to use the natural log.
That's because of this. Right there. Okay. So. Okay. Well, let's try this negative 0.19 transformation. I'm sorry. First of all, I need to do one other little thing. Okay. Well, how did I know it was exactly negative 0.19? This is where it takes some additional R coding to figure it out. What I can do, we've done this before, I can type names, save.bc. This is where I'm saving the results from Box-Cox transformation. Notice I have two components, x and y. Basically, this is what's on the x-axis, this is what's on the y-axis of the plot that we just saw. So x-axis contains values of lambda, y-axis contains then the corresponding log likelihood function values. So if I say save.bc $x, I'm going to do a head with it first. Notice lambda equal negative 2, negative 1.99, and so on. In fact, if I did a tail, see that? Now if I did head save.bc $y, we see the corresponding, you can see this in the plot here, at negative 2, the log likelihood function was negative 41.299, where my mouse is. Well, what I like to know is Now, what was that maximum value that we see graphically here? What was the maximum value? So I can do max save.bc $y. The maximum value is negative 24.17. Take a look at the plot. Yeah, that seems to make sense. Now, though, I need to figure out, well, what was the corresponding value of lambda exactly that generated that? Unfortunately, the authors of the function, Venables and Ripley, don't make it easy to figure that out. But this is how you can do it. So again, save.bc $y contains all of my likelihood function values. And what I'm going to do is this, equal max save.bc $y. What that equal tells R to do is do a logical comparison. Compare each of the values in that y to the max. I get trues and falses. Where there was one true. Notice that corresponds to the 182nd element of what's in y. Notice how everything, there was, let's see, there's a total of 401, 98, 99, yeah, 401 different values of y, because there are 401 different values between negative 2 and positive 2 by 0.01. And the 182nd value corresponds to where that maximum occurred. So, what I can do is take save.bc $y, bracket 182, end bracket, and there's that negative 24.16. A more, I guess a better way to do this, though, is instead do this. What R is going to do is that wherever it sees a true value inside this logical comparison, it's going to return that corresponding value of y. When it sees a false, it doesn't return it. And so that's a better coding way to pull out then that negative 24.17. Alternatively, what I could do, how about if I change this to x now? What do you think is going to result? It's going to find the corresponding value of lambda that had that max for the log likelihood function, negative 0.19. So that's how you find that negative 0.19. Again, I wish that the authors of the function would have made it a little bit easier to figure out what that lambda hat would be, but unfortunately they didn't. And this is just how you could go about actually finding it. And the reason why we want to do that is because I'm going to put that negative 0.19 into an object called lambda.hat so that I can actually estimate my model now with the transform y. So volume, and then I'm going to do I'm going to use the caret sign there, lambda.hat. Now, interestingly here, I don't need the I function. Remember how we needed the I function whenever we were taking something to a power on the right hand for a predictor variable? I don't need that here. It's just the syntax. You can use it. It will work out fine, but you don't need it. Then tilde hat. I'm going to put the results into mod.fit2, summarize the fit, so that now my estimated model, let me actually write it out someplace. Yep, here it is. Here is my estimated model. I pulled out that B0 and that B1 from the output. Well, what about doing a residual plot then? So I do the residuals versus this transformed y. Do you see any differences in variability amongst the residuals as a function of the transform y? Yes or no? No? The answer is basically no. I think all of you agree with me. It looks better than what it did before. And again, you got to be careful with looking for trends that don't necessarily exist. And it looks like, generally speaking, that this worked. Well, how about lambda equals 0? As I said before, that seemed like that was a possibility because it was inside our confidence interval. And because of that, then it also allows us to work with a natural log transformation, which is more and more friendly to work with, you could say. More something that we're maybe used to seeing. So to get the natural log transformation, I use the log function. I can estimate my model like I did before. So that here is my new B0. Here's my new B1. Here's what the actual model then looks like. And if I were to look at then the residuals versus the log of y hat, what do you think? Does it look good?
Seems better then.
I don't know if it's better. I don't know. It seems reasonably the same, I thought. I don't know. Why do you think it looks better?
Because the previous one was like something.
Oops, sorry. Shame on me. I think this is the first time this has happened in my class. I have a little appointment that comes up in my calendar always before class, which is silence my phone. Obviously, I ignored my appointment today. I'm sorry. What were you saying?
Yes, I mean for the y hat like 0.9.
Yeah, on page 332. Compare that to the plot on page 334.
Yes, 332. It seems like you can have like something like a parabola if you look deeply.
If you look deeply? Well, I don't like to look deeply. I don't know. I guess I don't really see the pattern. I don't really see the pattern. But in the end, what I was going to say is that both transformations seem to work okay. If you don't like the negative 0.19 transformation, use the log. Okay? We'll both be happy. What would I do in practice? I probably would use the log transformation just because I'm more used to working with that kind of a transformation. It's easier to work with. So in this particular case, let's say that I wanted to write the model such that y hat is only on the left-hand side of the equation. What would my model look like? I have y hat here. What would go on the right-hand side? What's that?
E.
E, yeah, the exponential transformation. So E raised to the negative 0.7965 plus 0.0535 x power. So that's how I would actually find, in this case, my y hat. Now, why would you want that? Well, often, we want to do predictions on the original scale. If you tell someone that the log of your college GPA is 0.5, well, who cares what the log of your college GPA is going to be? You want the estimated college GPA itself. You don't care about its log. So that's why, in the end, you would always want to make that little transformation back. Let's go back to this example. Well, what would you do here? What's y hat? I want to be able to write my model as y hat is equal to something. Well, I don't know, depending upon your comfortability level, what you should do is take a look at a little bit easier example, just from my experience with doing this example in class. Suppose I had this, y hat to the 1/2 power is equal to b0 plus b1 times x. And I want to find y hat. So what would I do? Well, I could do something like this. Let's see. Actually, let's put that y hat to the negative 1/2 power. I could rewrite my model then as this, y hat, 1 over y hat to to the 1/2 power is equal to, I can't do algebra today. I can write this as y hat to the 1/2 power is equal to 1 over b0 plus b1 times x, right? Or equivalently, how about you could say b0 plus b1 times x raised to the -1 power. And then I just need to apply now the square root, or the opposite of the square root transformation, which would be square both sides, so that you will get this 1 over b0 plus b1 times x squared, or equivalently b0 plus b1 times x raised to the -2 power. Okay? Do the same idea here. I'll let you do this on your own, but please note that there is an error in the comment here. I know it's hard to see there, but what I have written is, b0 plus b1 times x, and I have written in the comment the answer, which is I think 1 to the, or I have this written. I need a minus there. Okay, I forgot the minus in my comments. Okay, lastly then, page 334, 335. So Box-Cox transformation, you know, it seemed to work well here. You know, I don't know, I sometimes will use it, sometimes I will just simply try the common transformations I talked about at the very beginning, the log transformation, the inverse transformation, square root transformation, see if I get a reasonable plot. Now there happens to be a function in R called viz.boxcox. It's in the teaching demos package, which is not, I don't think it's automatically installed in R. And it's kind of an interesting little function. If you just simply run the function like this and hit enter, it will simulate some data for you, and that will pop up a little plot like this, where you see the raw data in the upper left-hand side, and you can see that obviously some kind of transformation is probably going to be needed. And so on the right-hand side, upper right-hand side, they say, well, what happens if lambda is equal to 1? And then down below in the lower left-hand corner, they have the residuals. They're plotted versus x, but since we're only using one explanatory variable here, you'll get the same, it's still going to give you the same kind of information. And then, anyway, but the main thing is here, you got this little, what's often referred to as a slider down below. It allows you to see what would happen if you had different values of lambda. And so in this particular case, if I had lambda of, same simulated data as I was working with earlier. Let's see, what would be a good lambda? So I'm thinking like a lambda right around 0, which you can't get exactly, would suggest that you would have a natural log transformation. And if you look in the bottom right-hand corner plot, that's what I'm looking at here, you can see that now you're starting to get a random scattering of points. So you can play with it, this on your own. It's in the teaching demos package. It just gives you a little demonstration of working with the Box-Cox transformation. Okay. Are there any questions? And that is it for today.